Hi everyone, today we're going to talk about relative solubility and the common ion effect. This is tied to learning objective 6.22 and 0.23 from the College Board that the student can interpret data regarding solubility of salt, to rank them by solubility, and also to reason the relative solubility in terms of the factors such as common ion and pH. Relative solubility. Now here let's look at a table in which we compare the compound barium sulfate, strontium fluoride, and silver chromate in terms of the KSP. And as you know that silver chromate has the lowest or smallest KSP, where the barium sulfate has the largest KSP. But when we calculate the molar solubility, we use X as an expression, and we find the ranking to be the highest being strontium fluoride, followed by silver chromate, and followed by barium sulfate. The conclusion is that the KSP values can be compared relatively if their compounds have the similar dissociation stoichiometry. Now, if we look at strontium fluoride and barium sulfate, strontium fluoride has a smaller KSP than barium sulfate and yet a higher molar solubility. That means the relative solubility cannot be compared directly based on KSP because they have different dissociation stoichiometry. For barium sulfate, the KSP is equal to x squared, and strontium fluoride is equal to 4x cubed. However, with strontium fluoride and silver chromate, now we can compare their KSP directly to relate their molar solubility because they have similar stoichiometry in dissociation. And therefore, the strontium fluoride, being larger in KSP, would have a higher molar solubility than silver chromate. One of the effects that will interfere with solubility is called common ion effect. That means when a compound is dissolved in a solution containing one of its ions, and the presence of common ion will decrease the solubility. Let's look at a picture here. And on the left side, we have lead chloride, and the right side, we have sodium chloride added to lead chloride. And you can see the amount of precipitate is greater in the second test tube on the right-hand side. Now, let's say we have lead chloride, and to that we add 0.1 molar sodium chloride. So lead chloride is sparingly soluble. We write that at equilibrium. The equation is lead ion, and 2 moles of chloride ions formed. KSP is 1.6 times 10 to the minus 5. Now with sodium chloride, which is highly soluble in water, is almost going to completion, represented by one-way arrow. Sodium and chloride ions will dissociate. By La Chatelier's principle, the presence of chloride ion in the test tube in a solution will shift the equilibrium to the left. That means forming more lead chloride precipitate. That means a salt becomes less soluble in a solution that has a common ion. Let's do some calculation involving common ion. Here are the given situation, sodium chloride and lead chloride, and KSP of lead chloride is 1.6 times 10 to the minus 5, and let X be the concentration of lead ion. So initially we have nothing for the lead ion, but the chloride ion, because of sodium chloride, we have 0.1 molar. Now the change being X and 2X, and the equilibrium concentration is X for the lead ion, and 2X plus 0.1 coming from the sodium chloride for the chloride ion concentration. So we put it into the KSP expression. 1.6 times 10 to the minus 5 is equal to X times 2X plus 0.1 raised to the power 2. But we can say the 2X, or the X, is very small compared to the 0.1 molar, so we can drop the 2X from the expression. And solving for that, the molar solubility would be 1.6 times 10 to the minus 3 molar. Now let's compare that with pure lead chloride in a saturated solution. The molar solubility of that would be 1.6 times 10 to the minus 2 molar. Therefore, you can see that the molar solubility of lead chloride is decreased by about 10 times in the presence of sodium chloride due to the presence of the common chloride ion. There's another factor that would affect solubility, which is pH. For example, if we have magnesium hydroxide, milk of magnesia dissolved in water to form magnesium and 2 moles of hydroxide ions. If the pH is high, that means the hydroxide ion concentration is high, then by Le Chatelier's principle, the equilibrium will be shifted to the left and lower the solubility of magnesium hydroxide. If the pH value is low, that means we have a high concentration of hydronium ion that will neutralize the hydroxide ion and take it out of the product side. That means the equilibrium will now shift to the right-hand side to increase the solubility of magnesium hydroxide. In terms of real-life application, in mining, the natural water can be contaminated by the iron 3+ ion. And this iron ion will hydrate in water to form a complex ion, and this complex ion will dissociate to donate the proton, which makes the solution acidic. So the way to remove the iron ion is by adding the hydroxide ion, which will precipitate out the FeOH3 as solid, which can then be removed, and we can then remove this contamination from the natural water. Another application will be acid rain on carbonate. Now, rainwater is weakly acidic due to dissolved CO2. So the CO2 in water will form carbonic acid, and it will then ionize to donate the proton, making it slightly acidic. When this water flows through underground, the limestone, calcium carbonate will dissolve in it to form huge caves, according to the following equation. So you can see these interesting structures are formed because when CO2 escapes to the air, the pH of the dripping water will increase. That means it's becoming less acidic. So the calcium carbonate will precipitate out to form these interesting structures when water evaporates in a cave. Another effect that can change the solubility is called complex ion formation. The solubility of the salt containing transition metal ions, that means they are Lewis acid and they are electron pair acceptors. Well, they will increase, the solubility will increase if we have Lewis base, which are electron pair donors, such as ammonia, cyanide ion, or hydroxide ion, or chloride ion, because these complex ions will be formed to make the salt become more soluble. Now, let's take a look at silver chloride. It is sparingly soluble in water. So when concentrated ammonia is added to the saturated solution of silver chloride, it actually clears it up. It dissolves the silver chloride as in the diagram on the right-hand side, because the silver ion will interact with the ammonia and driving equilibrium to the right. So here's an equation. Silver chloride, a not very soluble solid, when added to ammonia, will then form the complex ion, which will dissolve the silver chloride. Let's take a look at the equation itself. Ksp is 1.6 times 10 to the minus 10. Now, let's write the first equation. Silver ion adding 1 ammonia will make the first complex ion, with K1 being 2.1 times 10 to the power 3. As you can tell from the K value, that is already quite soluble compared to what it was before. Now then, this first complex ion reacting with another mole of ammonia to form the final complex ion, AgNH3 2+. And the K2 again is 8.2 times 10 to the power 3, a very large value compared to the original Ksp. So when we add up the equation of the 3 together, we have the following equation: silver chloride and 2 moles of ammonia to form the complex ion and chloride ion. Now what do we do in terms of the K values? The overall K will be the product of 3 K values. When we multiply them together, we get 2.8 times 10 to the minus 3. Large K meaning greater solubility. Let's try to solve a problem involving formation of complex ion. Starting with silver chloride in 10 molar of ammonia solution. Now let X be the concentration of the complex ion and the chloride ion, as well as the molar solubility of silver chloride. According to the equation, we set up the ice table. We start out with 10 molar for the ammonia and nothing for the complex ion and chloride ion. We remove 2X from the ammonia. We add X molar to the complex ion and the chloride ion. And finally, at equilibrium, we have 10.0 minus 2X for the concentration of ammonia, and X and X being concentration of the ions. Now we set up the K equilibrium expression by having the product over the reactant, and ammonia we have to raise it to the power of 2. And then we let it be equal to 2.8 times 10 to the minus 3, the number that we calculated from the last slide, equal to x squared over 10 minus 2x raised to the power 2. So finally, X is solved as 0.48 mole per liter. This is the molar solubility of silver chloride in ammonia, and that number is quite large when you compare that with just by pure silver chloride. The concentration, the molar solubility is 1.3 times 10 to the minus 5. So we have greatly increased the dissolving of silver chloride by adding ammonia, which is a Lewis base. To sum up what we have learned today, we learned that the KSP can be compared directly as a measure of relative solubility if the solutions have same dissociation stoichiometry. We also learned that common ion will decrease solubility. We learned how to calculate the solubility involving common ion. We also learned that the pH will change the solubility and 2 real-life applications. And finally, we learned that complex ion formation will enhance solubility, and we also solve problems related to such. I hope that you have found the video to be helpful. If you like it, please give us a like. And I look forward to seeing you in part 3.